mechanism of current. In the mechanism of current, we will discuss about if EMF induced, then what is the use of that EMF, what type of questions or what is the utility of that EMF which we have found in the circuit. So, that is the main point we are going to discuss here. Okay, in the previous section we have done how many ways we can calculate the EMF and how many type of conductors are there in which the EMF can be induced. But after inducing the EMF, then what is the effect or how it can play the role in the particular circuit. See, just like if I am considering one of the example or one of the situation, and then see the role of the EMF here. I took here M and N, Mn and OP. These are the two parallel rails, and these two rails are separated by a distance L. So, Mn and OP are the parallel rails and separated by a distance L. If the let one end of the rails are short circuited by a resistance R, and a conductor is given, this is, let x dash is a conductor of mass m, this is given, and whole system kept in horizontal plane and magnetic field into the plane of the system. It means we can say it is just like this horizontal system. This is your one Mn your rail, this is your another rail, and these end of the rails are short circuited by resistance R, and conductor x dash is like this, and magnetic field into the plane of this whole system. Magnetic field directed inward, and whole system is your, we can say this is your horizontal plane, whole system kept in a system is in horizontal plane. Okay. After that, what type of questions can be asked here, or what is the scene here? Now, at t is equal to 0, let the conductor is given velocity v naught. At t is equal to 0, conductor is given a velocity v naught, and then we will find out or we will check it either the velocity of conductor remain constant, or it decreases or increases, or what will happen if we are giving a velocity to the conductor. See, so we are going to find velocity of a conductor as a function of time t. Velocity of conductor as a function of time t, or we are looking here Vt value. See, so first of all, see the effect of velocity v naught. So, what will happen as soon as the velocity v naught is given? So, magnetic field your inward, V cross B this one. So, a EMF induced. In this conductor, a EMF induced, and when EMF induced here, so this terminal will be at higher potential, this will be at lower potential. And how much the EMF value? That EMF value depends on the velocity, and in straight conductor EMF already we have known. So, EMF induced is written as VBL. This is the EMF induced, V is the velocity. So, due to the effect of EMF, this is your higher potential, this is your lower potential, a current will be there. That current is called your induced current. So, when current is there here, so that current will go through this conductor also. So, now this conductor can be said as a current carrying conductor, and this current carrying conductor placed in magnetic field. So whenever current carrying conductor placed in magnetic field, there is chance of magnetic force on that conductor. So see here, current in this direction, magnetic field your inward. So according to your F is equal to your, as we know, one force on current carrying conductor is given as ideal cross B. Ideal direction your this, B your inward, so magnetic force your leftward. So in that side, magnetic force start acting, and that magnetic force your opposite to the velocity V naught. It means now velocity of conductor decreases. So when velocity of conductor decreases, let at the new position velocity of conductor can be given as V, and we can find one magnetic force F magnetic, which is your IBL. So equation for that. So magnitude of F is your IBL, and I value we can have induced EMF by resistance into BL. So induced EMF is your VBL, so we can have B square L square by R into V. This is the force. So A is equal to your B square L square by MR into V. This is a relation for acceleration, but here that force you are acting opposite to direction of velocity, so that is the retardation in fact. So as here A is your minus dV by dt, and now we can simplify. A is value B square L square by MR into V minus dV by dt, and then we can write here minus dV by V is equal to your B square L square by MR dt, and now we can simplify. At t0 velocity of V naught, at tt velocity or V, we can have ln V by V naught is your minus B square L square by MR into T. This is the relation for velocity. So now further we can write V is equal to your V naught e to the power minus B square L square by MR into T. So from here it has been concluded the velocity of a conductor you vary with the time, and it vary exponentially. So after infinite time its velocity become 0. So if we want to see the graph how the velocity vary with the time, so we can have this type of relation like this. So this is the variation of velocity of a conductor. So that can be said as a mechanism of current, what is happening when current starts flowing. Now in this problem so many things can be changed, so many things can be done here, and we can have different type of problem. See, let for example, suppose in the same question here what can be done, let other end of the rails also join, and this time these are joined with a capacitor. Let's see. Okay, let for example, now the question is that, see, if the other end of the rail is joined with a capacitor of capacitance C, then if we have to write the or see the relation, then how to get that? See, in that case what will happen, as potential here you see a potential is your E is given as VBL, potential your VBL, or induced EMF in the loop is your VBL. So what I observe, C is in parallel with the EMF source. So in this some charge will be there Q, and as potential across this your continuously vary because V is changing, so charge will also change. When charge is changing here, so it means charge is flowing here. So let charge is flowing, so some current may be there. So let I1 is the here, and here we can say I2. So net I is this. So one equation we can have I is equal to your I1 plus I2, where I1 is your nothing dq by dt, the rate of change of rate of variation of charge, and q is your C into EMF. In the EMF, V is the only variable term, so it is written as BLC dV by dt. This is your I1, and then I2 here E by R, I2 here E by R, which is your VBL by R. Now equation your that. Now the force, magnetic force will be your I B into L, and I is your I1 plus I2. So I1 plus I2 written as BLC into dV by dt plus I2 your VBL by R. This is your F magnetic. So acceleration BL we can take common, and this is your I into BL. So B square L square by M we can take common here, then this is your C dV by dt, and this is your plus V by R. This is the acceleration, and after that this can be written as minus dV by dt, because in fact force acting in the leftward direction and velocity in the rightward direction. After that we can simplify. So minus dV by dt we can take common. So what we will get? 1, and this also come on that side. So plus B square L square C by M. This is your dV by dt, and which is equal to your B square L square by MR into V. Now again we can simplify this one and we will get answer. So minus dV by V is equal to your V square L square by R M plus B square L square C into dt. Integrate T0 velocity V naught, dt velocity or V, and we further simplify. So what is the main point here? The main point is this: when the capacitors are connected in that side, so there is nothing, any big change, only a small thing we have to do. This is charge on this capacitor is coming, so current start coming in that side. So due to that current, so total current will in the conductor will change, which is equal to your I1 plus I2. Accordingly we have made equation and we got the answer easily. Now see some example based on the mechanism of current. Now see, in this example, AB and CD are these two parallel rails which are separated by a distance 1 meter as shown. The one end of the rail are short circuited by resistance R1 and another end is here with resistance R2. The whole system kept in a vertical plane under gravity, and the G value you can take as a 10 meter per second square. It is under gravity. So what is the question here? Question is that a PQ conductor of mass 0.2 kg is released from rest under gravity, and now it is falling. And when it is falling, so when the PQ conductor attain a terminal velocity we can say the final velocity we can say when the velocity is further not changing. When velocity further not changing means net velocity of that your constant, or the net force on this will 0. So, it is given terminal velocity is there. So, at that moment the power dissipate across R1 resistance your 0.76 watt and power dissipate across R2 resistance your 1.2 watt. Then what is the terminal velocity and what is the value of R1 and R2? This is the problem here. So, we can say, so we can write here the conductor release from rest under gravity. So, when conductor receive or when conductor achieve terminal velocity, when conductor achieve terminal velocity, at that time power dissipates across R1 and R2 are given. So, find the terminal velocity, and value of R1 and R2. This is the question here. So, first of all, as I said, meaning of terminal velocity. Terminal velocity can be said as a final velocity. Final velocity means there is no further change in the velocity. No further change in the velocity means the net force on that is 0. So, first of all, we will check it. What are the forces acting on the conductor PQ? So, as soon as it released from rest, at that moment only mg is acting downward. At that moment only mg is acting like this here. The gravity is acting. Under the effect of gravity, it start coming down. It start accelerating. As soon as it accelerates, it acquires certain velocity. Because of that velocity, a EMF will develop, and see the direction of and polarity of the EMF. So, magnetic field your inward direction, velocity or downward. So, according to the rule, the Q terminal will be at higher potential than P. So, as Q will be at higher potential than P, so current will be here in that direction like this. So, current in this direction. As soon as current start flowing, this conductor experiences a magnetic force also. So, magnetic field your inward, current your rightward, so magnetic force your upward. So, what is happening here? All the things are going on simultaneously. So, simultaneously your mg start acting, immediately your F magnetic force is also there, and current is in this direction, and this is your higher potential, this is your lower potential. So, first of all, important point here, when we are talking about terminal velocity, the net force 0. It means mg must be equal to your FO magnetic. So, we can write, then we can get the idea about the what could be the terminal velocity. So, at terminal velocity, let that is your, I am considering Vt. So, this time it has a Vt. At terminal velocity Vt, F magnetic is equal to your mg. So, F magnetic here, as we know, IBL, mg, weight of this, I as we know, EMF by So first of all, I value here. I is your EMF. So I, whatever I here, some part of the I will go here, I1 and here I2, and all these three are in series. So I is written as I1 plus I2 BL mg, and I1, since these are in parallel, so I is your EMF induced, E 1 by R1 plus 1 by R2, BL is your mg, and E is your state conductor moving with velocity Vt. So induced EMF E is your at terminal velocity VBL, like this. So E is your VTBL. So E is your Vt 1 by R1 plus 1 by R2 BL, and B square L square is your mg. So this can be said as a first equation. In this equation we are having three unknowns: Vt, R1, R2, B square L square value, mg value. All values are given because B value given, L also given, M also given, and G also given. So two more equations required to solve this problem. For two more equations, we are having this relation: power across R1. Power across R1 is your EMF across R1 by R1. So see, as power across R1, so PR1 written as E square by R1. So that is given here 0.76, and E value your VTBL. So Vt square B square L square by R1. This is your second equation, we can say. Similarly for PR2, we can write in the same way: Vt square B square L square by R2. So power across R2 here 1.2, that is equal to again Vt square B square L square by R2. This is your second equation. Now we can do one thing: we can add these two equations, so that value we can get from here. So see here, from from second and third, from equation 2 and 3 on adding. When we are adding here, 1.96 equal to your Vt square B square L square 1 by R1 plus 1 by R2, and see here Vt B square L square, Vt B square L square 1 by R1, that is your mg. So this is nothing, it is your mg into Vt. So from here Vt value we can have 1.96 by mg. So m value is given 0.2, and g your, if we are adding 9.8, then I think we can get better option. So g is 9.8. So from here it's coming, that is your 0.2, or directly we can write your 1 meter per second. So this is the speed unit, terminal velocity Vt. After getting terminal velocity, substitute the value of Vt in this equation, B and L given, so we will get R1. And now we can substitute in this equation, we can get the value of R2. In this manner we can calculate all the values. So this is the just application of your mechanism of current. Okay, when the conductor start moving, then what is the effect? So see, when conductor move, So current starts flowing. Due to that, this type of phenomena can happen. Now see another example. Example number 2. In this example, these are two parallel rails, and the gap between the rails is given you 10 centimeter. In these two parallel rails, we are having two conductors PQ and MN, and the velocity of conductor PQ is given your V1 4 meter per second towards left, and on conductor MN velocity given your V2 2 meter per second in the rightward direction. So each conductor resistance also given. Resistance of conductor Mn is your 15 and resistance of conductor PQ is your 10 ohm. As well as these two rails are short circuited by a wire having resistance 5 ohm as shown in diagram. Now the whole system kept in uniform magnetic field which is directed into the plane of this system, which is directed into the plane of that, and that magnetic field is given as 0.01 Tesla. Now question is this: find the current across 5 ohm resistance. So now see, the question is that find the current across 5 ohm resistance. This is the problem here. Now see the solution. How to do this thing? See, as we know, these are our two conductors PQ and Mn. These two conductors are moving in magnetic field. Due to motion of these two conductors, there is an induced EMF. See here, if I am looking the PQ conductor, velocity in this direction, magnetic field your inward. See, by according to the rule, the P will be at higher potential than Q. So in place of PQ, we can replace one of the battery of EMF V1BL. Similarly, in Mn, velocity are in that direction. So M will be at higher potential than Q. See here, that whole system can be replaced like this. In place of P and Q, see, velocity over your this side and magnetic field your inward. So Q will be at higher potential. So we can have like this. This is point Q, this is your P, and let EMF is your E1, and since resistance your 10 ohm, so this value you are here 10 ohm. Now A and B are 5 ohm, so that can be written or made like this. This is your 5 ohm, and then M and N. If we are looking M and N, see, velocity are in this direction. So according to the rule, M at higher potential, M at higher potential, and here potential E2, and resistance of this here 15 ohm like this. Now we have to find current on this. So this is your simple electrical circuit. Now we will calculate the value of E1. E1 is your V1 BL. So V1 value given here 4, magnetic field B your 0.01, and L is your 10 centimeter means 0.1. We can say this is your 4 millivolt. Similarly, if I am looking the E2 your V2 BL, V2 value are 2, B is 0.01, L is 0.1. So this is your 2 millivolt. Now we will solve the problem like this. Let here current your I1. If this is current I1, that also can be taken as I1, and let this is current your I2. So here current your I2, here your I1. So So this current can be said as your I2 minus I1, then here your I2. Likewise, so we can check here. Now apply Kirchhoff law. So we can apply Kirchhoff law like this, and here also we can apply like this. We are starting from here. We are going in that side, current in this direction. So positive plus 5 I2 minus I1, and then plus E1 and minus 10 I1, which is your 0. So 10 I1 right side minus 5 I1. So we can say here 15 I1 minus 5 I2 is your E1, and E1 value are 4 millivolt, 4 into 10 to the power minus 3. This is your first equation. Similarly, we can apply Kirchhoff law here. We are moving from this side. So minus 15 I2 minus 15 I2 plus E2. This is plus E2. Then here minus 5 I2 minus I1, and this is equal to here 0. So we can substitute here value. We can bring in that side. So what will be the result? 15 I2 minus 5 I2. So this become your 20 I2, and then your, so 20 I2 minus 5 I1 is equal to your E2, and E2 your 2 into 10 power minus 3. This is your second equation. Now we can add just, so one thing we can do, so 1 plus 3 times equation 2. So when we are multiplying here 3 times equation 2, so this and this will cancel, 3 times multiply. So 20 into 3, 60 I2 here, 5 I2. So 55 I2 is equal to 3 I2, 3 2 just 6, plus 4, 10. 10 into 10 to power minus 3. So I2 is 10 by 55 milliampere, or 2 by 11 milliampere. This is your value of I2. Now we can substitute the value of I2 over here or any of the equation. So there, see, then I1. If I am looking the I1, so I1 can be said as your 20 I2 minus 2 by 5 milliampere. 20 I2 minus 2 by 5 milliampere, and I2 value is your this 20 I2 means 40 by 11. So 40 by 11, 11 into 2, 20, 2 by 11 minus 2 by 5. This will be your 18 by 55 milliampere. 18 by 55 milliampere, and I2 is your this. So current across 5 ohm. Current across 5 ohm is your I2 minus I1. So current across 5 ohm resistance, I2 minus I1, which is equal to your 2 by 11 minus 18 by 55, that is your minus 8 by 55 milliampere. The minus sign indicate कि rather current flowing in that direction, current will flow in the upward direction. So this is the one of the example based on mechanism of current. Now see another example. Now see another example. In this example, this is your 1/4 of a circle, or you can say a circular sector is given, and that sector is making an angle 45 degree here. And now this sector is free to rotate about O with angular velocity, uniform angular velocity omega. So what has been given? The upper part of this sector have magnetic field B, which is given here 1 Tesla, but there is no magnetic field in the lower part. And this circular sector have radius 20 centimeter, and the resistance of the whole loop is given 20 ohm, and the rate of heat generation in this loop here pi millijoule per cycle. It means when the loop is rotating and when it is completing one cycle or one round, then the how much heat generate, that is given your pi millijoule. So what you have to find? You have to calculate what is the angular velocity of the sector, as well as how much is the average thermal power dissipate. That we have to calculate. So see, what will happen when the loop is moving in that trajectory. So when there is change in the flux, when there is a change in flux, at that time only the EMF induced, and at that time only the current will develop, and at that time only the heat will generate. So see, so when the loop is just about to enter, at the time when loop is just about to enter, so when loop enter and when loop leaves, and when loop leaves the magnetic field, at that time only heat will generate. So see, as the total angle here 45 degree, so when the loop is acquire this position 45 degree here, then the generation of heat here stop, because no change in the EMF, and when the loop is here at this position, means from here to here, there is no generation of heat. Only heat will generate when it is just about to enter completely and when it is just about to leave. So how to calculate heat? So first of all, EMF. EMF is given as half B omega A square. So EMF is this much, and that value we can get. So that is your let E. So current I is your E by R. So rate of heat generation, heat is your I square R into T. Now I square means E square by R, E by R whole square into RT, or E square by R into T. So first of all, E square. E value we can get here. Half B value given 1 Tesla. 1 Tesla. A is given 0.2. 0.2 square into omega. So this is your 2 omega by 100, or omega by 50 we can say. So omega by 50 is the EMF, and resistance is given as 20 ohm. So current is your omega by 1000. This is your current, or we can say E square. E square means here omega square by 50 into 50 by R. R is your 20 into T. This is the heat. This is the heat when it about to enter. So how much time it will take? So omega square by 50 into 50 into 20 time it will take. Total angle your 45 here, here 45, total angle your 90. So time period by 4. So time of the cycle is your and by 4, and this time is your omega square by time your 2 pi by omega into 4. So omega and omega we can cancel, and this heat is per cycle given your pi millijoule. So this is your pi into 10 to the power minus 3. Now simplify. So omega is equal to your pi and pi cancel, pi into 10 power minus 3 into 50 into 50 into 20 into 4 by 2 pi, and this pi and pi just cancel, and this here 1 2 3 and this 3 0, 2 and 2 cancel, and this here 25 into 4 100 radian per second. This is the value of omega. In this manner we can calculate the omega. And now average thermal power. Average thermal power means total heat we found in a cycle your this much. Total heat is your this much, pi millijoule. So heat, thermal power. So thermal power is your the power we can say heat by time, T. The total heat already we have found pi millijoule, millijoule 10 power minus 3, and time of one cycle here 2 pi by T, 2 pi by omega, omega is your 100. So this we can calculate. So here 10 by 2 or 10 power minus 1 by 2 or 1 by 20 watt. So 1 by 20 watt means 0.05 watt. This is the power. So in this manner we can solve the problem related to like this. Now come to the next point or next theoretical point.